So welcome to the lecture. In the previous two lectures, starting from the Newton's theory of gravity, and after imposing certain physical restrictions, we have arrived at the Lorentz covariant generalization of it. And the equation that we obtained is known as Pierce-Pauli equation, which is linear in the field as well as in source. Basically, it's a equation for a linearized theory of gravity. So let's write it down once again. So we denote the Pierce-Pauli field by the symbol H, and H mu nu. It has two index. It's a symmetric rank 2 tensor, and it satisfies the following equation. Box of H mu nu. Box is the D'Alembertian operator minus we have del mu lambda nu, and then we have mu and nu interchange. This term, then we have del nu of this H, and this H without any indices is the trace of H mu, which we defined as eta mu nu up index contracted with H. How we define trace that we discussed in previous lectures. And we also have eta mu nu times this del rho del sigma H rho sigma minus box of H, and this is equal to some kappa times the T mu, trace energy momentum tensor. And we have determined kappa by taking the non-relativistic limit of this equation, and in that limit we look at the 0, 0 component of this equation and identify the H00 with that of the Newtonian potential up to some factor of 2 and speed of light at vacuum, that is c, and so. And we can then determine the value of kappa, and which turns out to be dependent on the spacetime dimension, and in 3+1 dimension it is nothing but 16 pi g Newton by c, or 3+1 dimension. Now we have also stated that this equation enjoys an invariance under a gauge transformation of this Pierce-Pauli field. That is, if you make this H mu nu to some H mu nu prime, I am not writing explicitly that these are all function of x, these are fields, so it should be understood. So now if H mu nu goes to some H mu nu prime, which is related to H mu nu in the following way, then we can show that under this transformation, this equation remains invalid. Please do that exercise by yourself to get familiarized with the algebra. Now you can see that this is nothing but a generalization of the gauge transformation that you have seen in the context of electrodynamics, where the gauge transformation is generated by one single function. Instead, here we have 4 such functions, and together they form this 4 vector, which is denoted by this capital lambda, and it has this mu index which takes 4 values. That's some 4 arbitrary functions of coordinate. Now what we are going to do is that just like electrodynamics, we coupled the background electric and magnetic field with a point charge. We're going to try couple this Pierce-Pauli field with the matter. And just like electrodynamics, again, we expect that any such coupling is to be consistent not only the with the Lorentz transformation, also it has to be consistent with this underlying gauge transformation. That is the equation or laws of motion that we will get from those kind of coupling with matter should respect this underlying gauge invariance coming from this gauge transformation of the Pierce-Pauli field. And if you demand that, there will be several interesting consequences, which will be very important for our understanding of the nature of gravity. So we will discuss one of them in this lecture and the other one in the next lecture. So what we are going to see is that if you try to couple this h mu nu with some matter and demand that this coupling to be consistent with this gauge transformation, that is the underlying equation to be invariant under this gauge transformation, we will see that it is not enough to just to transform this h mu nu, but we have to transform the space-time coordinate also. So the space-time coordinates needs to be also gauge transformed with the same set of functions is capital L. So let's see how. What we will do is that we will try to couple this h mu nu with the matter source, which is nothing but a point particle of some mass. Okay. So again, we will follow the same approach as what we have taken when we are discussing these things in the context of electrodynamics. So first we will start with the Newton's second law for a point mass moving in a gravitational. What is that? So this is dp dt is equal to minus m times gradient of Newtonian potential phi of m. Now we wanted to first make it Lorentz covariant. So what will? So on the left hand side, we should replace it by for momentum dp nu. So coordinate time, we should have the proper tau. Then this side will behave as a forward under the Lorentz transformation. On this side, right hand side, we propose that the Lorentz covariant generalization of this term is nothing but the following: half m alpha beta delta mu. Again, remember that the direction of p, this momentum, is governed by this del, right? So the free index correspondingly, the free index on mu will be the free index on the partial del mu, and then the two index of h alpha beta should be contracted. We contract in the 4 velocity. Is the 4 velocity. Velocity component. Okay. So remember that this is basically dx alpha d tau, which is nothing but the zeroth component gamma times c. This is the gamma times the free velocity, that is the velocity with which respect the point particle is moving in the lab. Now you can easily see that if you take non-relativistic limit, then only the 3 component of it matter. So this, you take the spatial component, and in the non-relativistic limit, remember gamma is close to 1 because v is very, very smaller than c. So t and tau is basically same. So from this side, if you look at the 3 components, so it will be dp dt, and this side u0, if you look at the u0, which is basically c, and the ith component are these coming from this 3 velocity, which is very small. So in this sum, it will be dominated by where you have alpha beta 0. So you have half m c squared del of I h00, and h00, remember we have identified with the Newtonian potential in the following way. 0, 0 is nothing but 2 by square I of n. If you plug this here, then you will see that it will give this equation in this non-relativistic field. So kindly go through this logic once more time by yourself. But nonetheless, this is the correct Lorentz covariance generalization of the Newton's second law for the point particles moving in a gravitational field. But remember, we need to make sure that this equation remains invariant under the gauge transform. Of course, you can see that because we have only del mu of h alpha beta, and h alpha beta will transform in this way, this will not be an invariant under the gauge transformation. So we still need to make it invariant under the gauge transform of the first Pauli H. So remember that if we wanted to do that same exercise for a point charge particle moving in a background electromagnetic field, then the corresponding equation give rise to the fact that this side, instead of the kinematical momentum, we must have the canonical moment, which gets a contribution from the background field, that is mu for the electrodynamics. So we believe that same thing will happen, because here also this point mass is moving in a velocity dependent field. So which is obvious from this term. So this must be coming from some potential which is velocity dependent. There is a factor of u here, and then we also naturally expect that this side should be the canonical momentum, which we denote by pi mu instead of p mu nu, the kinematical momentum. So we expect that we need an equation of this form, p mu half m where pi mu nu is the component of canonical moment. Now let's check whether this equation remains gauge invariant or not. If not, what needs to be done? And before even going to check that, we need to know what is pi mu nu, the canonical momentum for this case. So now to fix or derive pi mu nu, we resort to a Lagrangian formula. So let's assume that this equation for a point mass moving in a linearized gravitational field or Pierce-Pauli field can be given or derived from a action principle, and the corresponding Lagrangian takes the form that some function of the coordinate x alpha u beta, and from this you can have the Lagrange equation d tau of del L u mu equal to del L del x mu. Now what can be this Lagrangian? So remember that this L we can take as some L0, that is the Lagrangian for a free point particle, and that is just half m times u alpha basically u square, relativistic velocity square. If you have just L0, you can find the equation of motion and you get the point particle equation of motion in its relativistic form that we discussed earlier. And then we'll have minus some v, because now it is moving in a gravitational field, which will see a potential, and v in general it's a velocity dependent potential, and we expect that this should give rise to other term, the interaction term between the point particle and the gravitational. Okay. So in general, v is the function of x alpha, and let's say some beta, relativistic formula. Okay. Now, if you compare this equation with what we wanted to get this, right? So let's write it one more time. So we have d pi mu and tau of m u alpha u beta tau mu h alpha beta. So if you compare these two equations, so this equation del L mu should give the rise, and dd tau of it should give rise to the rate of change of the canonical momentum, and this term should come from this del x mu, which basically gives you minus del v del x. So comparing these two, we get and the following: del L del x mu, which is nothing but minus of this, because L0 does not contain any x, del v del x mu is equal to half m u alpha u beta del mu is right. Now from here, you can basically integrate it out. Okay. So if you integrate this out, then you will get v as a function of some x and u is equal to minus half m u alpha u beta plus some integrating constant, because you are integrating with respect to x. So there will be some arbitrary function of only u. Right? So please do this exercise to show explicitly that this is indeed the case. What you have to do is that you can realize that this side you can actually write as del of x mu of this thing, m u alpha u beta h alpha beta. We are working, remember, in linear order in h, and that will essentially able to help you to write that del of this everything, then you just integrate. Now, how to fix this integrating constant? So remember that when h equal to 0, it's just a free particle, no potential. So v has to vanish. So when h basically equal to 0, some index, some all the component of H. There is no gravitational field. E has to vanish. That implies F of U. It should be big. So now we have our Lagrange. So let's write it down. L x alpha some U beta minus M some U square U alpha contracted, and then we have plus half M alpha U beta H alpha beta. And that comes from the V. So V is minus of this. So L is L minus V. So V plus. Now, from our Lagrangian mechanics, we know the definition of the canonical momentum is simply mu nu del L mu nu. And given this Lagrangian, we have M mu plus M H mu beta. So because this is quadratic in mu, this is also 2 mu. So this, if you properly do this partial derivative, so there are 2 term and they will add, and this half will go. Okay. So now this should be the correct momentum that we have to replace the kinematic momentum with in the point particle equation. And you can see that this is the kinematical piece, and this is the piece that is coming due to the fact that there is a velocity dependent potential, that is this field H mu is actually coupled with. Okay. So now in the point particle action, or rather in the point particle equation of motion, we have du d pi d tau of this thing. So we'll have d tau of M mu. Sorry, there should be index down here, as we are writing it in terms of the Bavarian index, pre-index H beta. This is d pi d tau, and this side of the equation gives half M U alpha U beta then mu alpha. And let's write it by expanding left hand side. So we have one term which is du d tau, and we have divide everything by the small n to get rid of that factor, and then you have from this term, one term is simply d u beta d tau H mu beta, and then we can bring this term here and note the fact that d tau after using the chain rule is basically del alpha dx alpha d tau, which is nothing but u alpha. U alpha is a tangent vector. And then you can use symmetrization of these indexes coming from d tau, this alpha index with the beta index, and then combine with this term. You can rewrite it this way: u alpha beta delta alpha H beta plus delta beta alpha minus mu H alpha beta equal to is the entire thing equal to 0. So this is just algebra, you should do it. So again, just to iterate myself, d tau of h mu beta, we will write as u alpha del alpha of h mu beta, then you symmetrize the index alpha beta, that will give you a half, and then you can combine this, you have this combination. So why I'm writing this way, it will be very clear shortly. So now remember that we are working only at the level of linear in h mu Pierre-Pauli. So now d u alpha d tau is the acceleration, and that should be proportional to derivative of the potential, that is h. So it should be proportional to something like a beta. So du d tau is actually order h itself, and for our case h mu nu is very, very less than 1. That is the assumption that we are making. So this term is of the order of h square. Right? All other term, the first and the last term, linear order in it. So we are going to neglect this term and finally get d mu d tau plus half q alpha beta alpha h mu beta plus alpha and beta interchange alpha minus del mu h alpha beta equal to 0. And let's put d mu is equal to this thing. I'm just lowered the indices, you can raise the index as well. So then we'll have, after raising the indices, the free index of mu, we have e square mu plus correct the alpha h the beta the mu equal to, you can rewrite in this. But if you look at this combination, we'll still see that this is again not, at least apparently, is not a gauge invariant. So if you do a gauge transformation, that is, if you take your h to h prime, which is related to h mu nu by del mu lambda mu nu, then you can show that this particular combination, let's call this as a alpha mu nu beta. So then a prime alpha mu nu beta will be is equal to, a prime means this will be made up of h prime, the new field after the gauge transformation. So in terms of the old field h, then this combination will look like beta minus 2 tau. Okay. So now if you have this equation du mu d tau after the gauge transformation of some 2 alpha beta beta A prime is equal to 0. This will give you, in terms of the old field H, du mu d tau plus half u alpha beta A sum. And then, so this half and this half will cancel. You have u alpha, u beta, del alpha, del beta, del mu. So now we have to analyze what is this extra term is going to do. Remember again that we want this point particle moving in a gravitational potential to be invariant under the gauge transform. Now, if you do that, same that there is this extra term which is in this shown in this red box. Now let's analyze this. Okay. So after a little thought, we can see that this term is nothing but the following. So let's start with this dd tau. Tau is the proper time. Now this is dd tau, and now replace this by chain rule. dd tau is equal to alpha tau and now it will have two terms. One is du alpha d tau, and another will have u alpha dd tau of this. Now again, du alpha d tau is of the order h because it's acceleration proportional derivative of h, so it's order h. But if you remember our gauge transformation, from here it is apparent that lambda is also of the order h. Actually, these terms are sum, right? H mu nu and del mu lambda, these are sum. So lambda is also order h. Which means as we are working only linear order in h, then we can neglect this term because this is order of h. And of course, again, we can use the chain rule here to write this as u alpha, u beta, del alpha, del beta of this. So d square del mu nu d tau square is basically u alpha, u beta, del plus of order h square term, which we are going to neglect. Now let's come back to the original equation, which is this, right? And after gauge transformation, this will have this additional term. And now we're going to replace at the discarding the order h square term, this term in the box by d squared lambda mu nu d tau square. And remember that this is nothing but d square x d tau square. So let's write it down. D square x mu d tau square minus d square capital lambda mu d tau square plus half u alpha u beta, and this is contracted with this combination alpha beta plus alpha beta interchanged alpha minus mu alpha beta plus some order h square term which we're going to neglect. We got it. Now we can see from this equation that this equation we remain invariant under the gauge transformation of this linearized Pierce-Pauli field. We also need to gauge transform the coordinate by the same set of these functions, capital lambda. So only under the joint transformation of h and the space-time coordinates, this equation will remain invariant. Let's write it down. We'll have x mu goes to some x prime mu equal to x mu plus lambda mu, which is some arbitrary function of x, and we have h mu nu x goes to some h prime mu nu at x prime equal to h mu nu x minus lambda mu del mu of lambda nu x minus del nu of lambda mu x. So when we do this transformation, this term generates this term linear order in h, and then if we would have done the transformation of x, then we could have absorbed this extra term in the transformation of the coordinate itself. So we need to perform a gauge transformation of the space-time coordinates in this way. And just to reiterate, here the lambda mu nu gives you a four set of arbitrary functions, and this contains the information of this gauge. So to make the coupling of a point particle consistent with the underlying gauge symmetry of the Pauli-Pierce field, we need to have this joint transformations. So the gauge transformation of the Pauli-Pierce field necessitates gauge transformation of the space-time coordinates. Need joint transformations. Okay. Now, if you look at this first line of equation, you can see that if this capital lambda would have been constant for vector, then this would have been just a usual translation. And we know that translation is symmetry of the Minkowski space. Now we have made this for vector components of it function of x itself. So what we have done is that now we have gauged the space-time translational symmetry. And that's the important lesson that we learned from this exercise, that to have an consistent coupling of a matter with the gravitational field, which respect the underlying gauge symmetry of this gravitational field, the space-time translational symmetry has to be gauged. Space-time translation symmetry is gauged. Now one can actually make this argument much more concrete by extending this analysis in higher order in H. One can repeat the same exercise and order by order in H and find the corresponding non-linear version of this set of these gauge transformation rules that we have written down. But we are not going to do that here. Instead, in the second half of the course, we will develop the formalism based on the Riemannian manifold, and then we will write down the nonlinear version or completion of this equation in just one step. So one more important lesson that we will learn from this exercise of coupling a point particle with the gravitational field is that we will see in the next lecture that this point particle will now see a different background metric than Minkowski metric. So that we will study in our lecture. We will end here now, and thank you for listening.